of course, we learned in Calculus 1 that there are a lot of applications for the derivative, but one of the big ones is a tangent line problem. So remember from Calculus 1 that when we have a real valued function, y is equal to some function of x, then the slope of the tangent line is equal to the derivative at that particular value. So if you want the tangent line at A, the slope of that line, the slope of that tangent line, would be equal to the derivative at that value. Okay, well, so how does that change for a vector valued function? It's modified a little bit. So you still have A right here, but this is t equals A. And so your tangent line comes like this, and it's not a line, it's a vector, right? So your tangent vector points in the direction of your motion. And the direction vector of that tangent would be equal to the derivative at that particular value. The derivative of the vector value function, of course. So this isn't quite slope, right? It's the direction vector, right? They're related, but they're not the same thing, right? So this is the direction vector of the tangent. And it could be a tangent line, it could be a tangent vector, it depends on what you're trying to do. All right, so let's look at a couple examples and kind of recap that. So this piece is a review of Calc 1. So this is a review of Calc 1. There's no vectors in this. So it says find the equation of the tangent line to the graph y equals square root of x at the point where x equals 1, which is right here. So I can see that there's a tangent line right there, and I want to find the equation of that line. Okay, well, I know that the slope of that tangent is equal to the derivative y prime at 1. Okay, so for my first mission, I'm going to find the derivative of x. Now, y is equal to, you'll note, x to the 1/2 power. We learn in Calculus 1 that we don't actually like writing square roots. It's way more useful to us to write them as a power because it makes the derivatives and the integrals easier. So the derivative would be 1/2 x to the negative 1/2. Or if you will, it's 1 over 2 square root of 2. Or square root of x. I'm sorry, square root of x. Okay, so then y prime at 1 would be 1 over 2 square root of 1, which is 1/2. So this is the slope of the tangent line, 1/2. Okay, well, to find the equation of a line, I'm going to need two things. I need the slope, which I have, and I also need a point on the line. Well, I don't have that yet, but I need one. So let's find that. So let's find this point right here. And this is the point of tangency. It's the point where the curve and the line, the one point that the curve and line had in common. So the point of tangency would be equal to 1 comma f of 1, or y of 1 in this case, because this function's just named y. So that would be 1, and then the square root of 1, which is 1, 1. All right, so now I have a point and I have the slope. So now let's see if we remember. I'm just going to write these over here. Recall. There's two main equations. Actually, there's three, but there's y minus y1 equals m times x minus x1. That's the point slope form. There's y equals mx plus b. That's one we use probably most often in algebra class. And then there's ax plus by equals c, which is standard. So this is point slope, that one. This one's slope-intercept. And this is standard. They all have their uses. In algebra class, we use the y equals mx plus b, but in this case, the y minus y1 would be more useful to us, this one. So we can say, well, y minus y1, which is 1, right? Because what you're doing over here is figuring out your x1 and your y1, right, for your point. So y minus 1 equals 1/2 times x minus x1, which is also 1. So this works. I'm sorry, my dog is barking. This is the equation of a line that is tangent to this curve at the point 1, 1. So now this form's kind of strange, so a lot of students don't like it. They prefer slope-intercept because that's what they're used to. So if I distribute the half, that's 1/2 x minus 1/2, and then I'd add 1 to it. So that'd be y equals 1/2 x plus 1/2. That would also work. Okay, so we found the equation of the tangent line. This blue line right there, that's the equation of the line. Okay, now how does it change when it's a vector valued function? So let's find the equation of the tangent line to the graph of r of t equals t comma square root of t at the point where t is equal to 1. Okay, so t is equal to 1. We're going to have to figure all this out, but let's start with our direction vector. So the direction vector, which is v for the tangent, would be equal to r prime. So r prime of t, let me just start with that. I'll start with the basic one. Okay, so r prime of t is equal to the derivative of t, which is 1, and the derivative of, there it is again. This is really t to the 1/2 power, and we prefer to write it that way, right? So t to the 1/2, because, right, so this is r of t. And we prefer to write it that way because it'll be easier for finding the derivative. Because the derivative of that, you bring the 1/2 down, you use the power rule. 1/2 t to the negative 1/2. And if I wanted to write that another way, it would be 1 over 2 square root of t, and that should be looking familiar to you. Because, of course, these two problems are related. Sorry, I don't like how small that was. There, I still didn't like it, so I rewrote it. Okay, so this is the direction vector for all the tangent lines. So this is for all tangent lines. Now, if we want the specific one for this one, then the direction vector for this particular tangent line would be at t equals 1. So that would be r prime at 1. So that would be 1 and then 1/2. Looking familiar, right? Because if you think about it, right, 1 comma 1/2 is the direction vector, right? Rise over run, right? You got your rise, you got your run, right? It works. They're related. They're not the same thing, but they're related. Okay, now I need another point. So I know my direction vector. I need a point on the tangent line. All right, well, a point on the tangent line will happen at the particular t value I was given. So if I just substitute r of 1, I would get the square, or excuse me, 1 comma the square root of 1, which is 1, 1, which should also be looking familiar to you. All right, so putting it all together, my tangent line, which is a vector, I'll call it L of t with a vector symbol over it, is equal to my direction vector, which was 1 comma 1/2 times t plus my point vector, which is 1, 1. And there we have it. Right? That is the equation of the line vector form. It's a little strange to write it that way, so usually we write it in pieces. So 1t plus 1, so t plus 1, 1/2 t plus 1, like that. That's the more common way to write it. And if you look at the graph, what you're finding is this piece right here. You're saying, hey, at the point 1, 1, it touches, right here, the point 1, 1. Of course, it's technically a vector pointing to that point, but that's your point, 1, 1. And then you have a direction of run of 1, rise of a half, right? Horizontal, vertical. So that gives you that. But this vector is, of course, free. So there's a line that's pointed out by that vector right here. Right? So that's the tangent line. This vector can move anywhere along that line.